Cool, thank you very much. And thank you to Jacob for organising and inviting me and so on. And thanks to everyone for attending on the last day of a very, last talk of a difficult day. Okay, so yeah, my name's Martha Lewis. I'm based at the University of Amsterdam. And I'm going to be talking about one or two compositional approaches to modelling language and concepts. I'm not giving a kind of overview of a bunch of different things. So what are my motivations here? So basically, large language models, vision language models, and so on are very, very impressive at the moment. So here I asked for a picture of 7 teddy bears engaged in writing poetry. Here I asked for, how to do a bar chart, because I couldn't quite remember the syntax and so on. So, does anyone notice anything? Yeah, it's only 6. Yeah, so they're impressive, but they make mistakes basically. And the idea is that hopefully using, potentially using like sort of compositional approaches, maybe similar to the sorts of things that Sean just outlined. We can help to sort of guard against this sort of thing. And you might say, well, it doesn't really matter because all you have to do is just check the output before you actually release it. But in fact, that doesn't happen. So this is from a few months ago now, but you probably remember all these like scammy AI-generated books. There was this ChatGPT chatbot that Chevrolet used that was selling cars for $1. There's a whole bunch of plagiarized papers on archive, and so on. So these outputs that are potentially wrong just don't get checked. And so this is the motivation for trying to come up with trying to at least diagnose ways in which these things might go wrong. More motivation. So why am I interested in these compositional approaches? So by compositional approaches, I kind of mean approaches that are going to use symbols in some sense and compose them according to some rules. And then there's going to be a kind of probably some kind of neural or statistical substrate under that. So these kinds of approaches can be better at certain kinds of problems. A lot of them are designed to actually model aspects of human reasoning, right? Whereas large neural networks are not designed to do that. They're potentially more interpretable and potentially provide ways to interpret what large neural models are doing. Okay, so here's an outline of the talk I'm going to give. I'm going to start. So my general background is actually or for a few years at least, has been in working with the kinds of model that Sean was describing. And a couple of these things that I'm going to talk about will be based in using those kinds of models. So this section on vision and language, the section on ambiguity and metaphor. But before that, I'm going to talk about some more recent work in analogy, which is a bit more diagnostic. It doesn't actually propose any particular model for analogy. It's more about diagnosing the limits of GPT-based models in solving analogy. And then, so I'll talk about that. I'll introduce a couple of compositional approaches to language, one of which is similar to what Sean was talking about, and then apply those in vision and language, ambiguity and metaphor. And then I'll just mention some things that I'm also interested in case anyone would like to chat about some future work as well. I might not get through all of these, so I might skip 1 or 2 of these sections. Okay. So the work on analogy, this was carried out with Melanie Mitchell. We recently presented it at CogSci, and it's available at this paper here. So what's the question we're answering here? So basically, about a year or so ago, Webb, Holyoake, and Liu released this paper saying that GPT-3 has this emergent ability to carry out analogical reasoning. They tested over a bunch of different analogy types. And what we're going to concentrate on here is just one of these, which is letter string analogies. So yeah, this you can see here these dark blue bars are GPT performance on these different tasks. The light blue bars are human performance on these different tasks, and so we can see that yeah, GPT is pretty good according to them at these things.
And are those dots individual performances?
Yeah, the dots are individuals, yes.
I would expect the error bars to look bigger with that.
Yeah, no, that's a good point.
The error in the mean.
Yeah, it's just that error.
Okay.
That's what people play.
Okay, so we're just, in this talk, I'm just going to talk about letter string analogies. So what are these? These were introduced by Hofstadter in 1994. And they look like this. So we have a question like if A, B, C, D goes to A, B, C, E, what does I, J, K, L go to? So any answers? Anyone want to?
M.
Just M?
I, J, K.
I, J, K, M, yeah. And that's what a lot of people answer. Some people also answer I, J, K, E, okay? So the rule there, so, you know, you had a rule that you used to produce this I, J, K, M. You know, the rule here would just be replace the last letter by E, which is kind of somewhat less satisfying in some ways to me anyway, but yeah, you know, it's but the most common thing that people come up with is this sort of answer, is the this successor answer. And so Webb, Holyoake, and Liu, and also we looked at these different task types. So we have a number of different task types, which are laid out here. So we have, here's one, extend sequence. So you can fill in the blanks for yourselves. So we have here A, B, C, D goes to A, B, C, D, E. What does I, J, K, L go to? Successor, which is the one we just saw. Predecessor, we have B, C, D, E goes to A, C, D, E. Remove redundant, so in remove redundant, we've got this extra like repeated letter somewhere, and the task is to take that out. Fix alphabet, so we've got a string which is not a substring of the alphabet, and you have to kind of repair it so that it is a substring of the alphabet. And then there's a sort problem as well. And in sort, there's only ever, in these particular problems, there's only ever 2 letters that have been permuted. Okay. And so what our tactic was to say, okay, well, if abstract reasoning ability or analogical reasoning ability really has emerged in GPT-3, then this ability ought to be there if we kind of change the context a little bit. And so we built a set of so-called counterfactual tasks, which in this case were basically doing the same kind of analogy problem, but with slightly permuted alphabets. Or, well, we actually range. Okay, so with permuted alphabets, and we have alphabets with progressively more letters out of place. So we start with 2 letters out of place, then we do tasks with 5 letters out of place, 10 letters out of place, 20 letters out of place. So with 20, it's almost completely sort of scrambled. And we also do a symbol alphabet of 10 symbols. And to check that the GPT models are actually able to kind of read the string that the alphabet string that we give it and sort of parse that, we do this counterfactual comprehension check, which in this case is just says, okay, if I give you this letter, what's the letter before it? What's the letter after it? And all the models pass that very well, apart from there was one, I think, on like 5 letters permuted, GPT 3.5 wasn't very good, but apart from that, they were all up at like 95% plus. Okay, so this is and so what we did was we gave a bunch of these problems to humans, a bunch of these problems to GPT-4, and we wanted to compare the performance. And this is the sort of thing that we gave to humans on prolific academic. So here we've got an example of the problem. So we give the humans the alphabet. This is an alphabet where we've just changed two of the letters. We've swapped the letter M and the letter E. So they've been swapped over. And then we give them a problem, and they just have to type the answer in this box, basically. And yeah, so in the human experiments, we gather data from 136 participants. Each participant completes 16 tasks. So this is one task. And they complete one of each of the type of tasks that I showed earlier, each with two different numbers of letters permuted. So, two letters permuted and then 10 letters permuted, something like this. We give them two with symbol alphabets and then two attention checks as well. And then for GPT experiments, we try out a number of different prompts, including one that was quite similar to the sort of human stimulus. The best results we got with a prompt like this, which was taken from these guys, Hodel and West, who had done a similar sort of a kind of smaller experiment in this vein. And we said, so we gave it a system prompt saying, you are able to solve letter string analogies. Use this fictional alphabet, and we give them the alphabet. Let's try to complete the pattern, and then we give them the pattern that they have to complete. And yeah, so we tested some other prompts as well. And so here are some results. So first of all, this is the human data that we got. So the blue lines are, the blue dots and lines rather, are from the original paper, from the Webb et al. Paper. These are UCLA undergrads. So, and our ones are the prolific participants. So, yeah. So first of all, we get better human results than them. There are reasons for that. So, their problem task setup was more difficult than ours. They gave them more. Questions, and they also gave them a range of kind of more difficult questions. We were only testing on a subset of the easier questions. Yes.
I'm curious. So in the right-hand side there,
yeah.
Is there like some other the 50% or 80% that are wrong? Are they concentrated on one alternative, or is it all over the place? Like, is the issue here is the issue agreement, or is the issue that half the people all get it the same way and the other just?
I don't know actually. I don't know. So you mean like where people are getting it wrong? Are they all getting it wrong in the same way?
Well, you're deciding what's right here, right? I don't know. This is maybe they're all right and you're wrong. I mean, and this is kind of funny.
Yeah. So I'll discuss that a little bit later on as well. But yeah, to be honest, I haven't looked at these human results like to categorize exactly what mistakes are being made. I mean, I have done that a little bit, but yeah, I don't know is the answer. That would be good to look into. Yeah.
Sorry, so
Yeah.
does everybody see all the tasks, or do you give them separate tasks?
All the tasks are mostly pretty different. They get a random selection of tasks, so there might be a little bit of overlap, but there's quite a lot of tasks. Yeah. So basically, every person gets one task from each category with alphabets with one number of letters permuted, and the alphabet is different every time. So it might be like B and Q are swapped, and then the next one M and E are swapped. So they get one of each sort of task for one, and then another lot for another number of letters permuted in the alphabet, and then just successor and predecessor for these symbol alphabets as well. Yeah. Yes.
Do the participants know that there are these 6 categories of tasks?
No, they have to work out like what the rule is. Yeah, I mean they might have come across this sort of task before, for sure, but yeah, we don't tell them. We don't say that. We don't say this is the sort of thing that we want you to do. Yeah. So our figures here, we're only comparing with the subset of the Web et al. Data that is for the same problems, but the Web et al. Participants had to do harder problems as well mixed in, and they had to do more of them. So this is probably why they're a bit lower. Okay. When we give the same sets of problems to GPT models, we find the following. So this is now on the x-axis, we've got numbers of letters permuted. So with no letters permuted, like with the standard alphabet, our humans are already doing a fair bit better than GPT. And then as we start mixing up letters in the alphabet, human performance remains roughly stable across these numbers of letters permuted, whereas GPT models kind of fall off. And particularly for these symbol alphabets, they really weren't able to sort of process that very well at all. Yeah?
For any given number of letters permuted, did the problems presented always include the permuted letters?
Yeah, always. Either in the example, so there's, the ABCD goes to ABCE, either in that bit or in the bit where they have to generate the answer. Yeah.
So I would also expect that GPT-4 would perform better.
Yeah.
Apparently GPT-3 is better here.
Yeah, yeah. So I'm not sure why that is. Possibly because GPT-4 is trained more for chat and so on, which maybe detracts from its sort of pattern completion abilities.
They had catastrophic remembering.
Yeah. Forgetting, catastrophic forgetting.
No.
Yeah. Yes.
It seems to me that if I take a mechanistic view of transformer network, which is what all these models are, I understand that they are trained in sequence completion, that they are very elaborate, high-dimensional, filled with lots of data pattern matchers. So my hypothesis upon starting would be that that the models will not be successful with your permuted alphabets and your counter examples to the ones that came in the original paper. What made those people think that there was something emergent or something else from the networks that was mechanistically different from how we would view the model with its transformer networks and training schemes?
Well, I think to pull together the sets of data sets to test GPT-3, it is, first sort of set of results, it is fairly surprising that they can do these things, right? I mean, GPT-2 couldn't do this.
But was there a claim that there was something emergent arising from the networks? Was there a claim
the
structure that
the title was
that you couldn't anticipate?
Well, I don't know about the structure, but the title was literally like emergent analogical reasoning in LLM. So yeah, that is what was being claimed.
If I can make a comment, we have a paper called Embers of Autoregression.
Oh yeah.
It was a response to the SPACs of AGI paper that makes this point. You can very easily get non-intelligent sorts of behaviors coming out of these models if you give them tasks that go against that autoregressive objective. Yeah, which is this is a good example.
Right. It's not even like a cognitive psychophysics experiment. It's just a mechanistic mistake, a mistake about the mechanisms of the model, right, and training. to think that something's going to emerge beyond the patterns that you gave it.
I
Well,
think
but I
that's
mean,
not
I bring it up because
That's
some
a
people
strong-
truly believe there's
Yeah.
something emergent,
But-
and that's what I wanted to,
Yeah, I
that's
mean,
why
if
I
you-
bring it up.
I mean, if you interact with models, you certainly get things beyond what it's been trained on.
Yeah.
You could very easily push it in that direction.
Yeah, I don't know what emergent means, but they definitely, you know,
I understand that they
generalize,
can
right?
generalize outside the samples they've seen, so I misspoke
Yeah.
if that was the intention.
Yeah.
I think I'm more referring to sort of the Sutskeyer hypothesis that there's some emergent structure in the network mechanistically that you can look at, right?
Yeah, I don't know if that is actually something that I would like to look at, as you know. Yeah.
Yeah.
So yeah, I think that would be cool. I don't know. Do you? Anyone else have any?
question here, and then maybe we'll go
Yeah.
back to the talk.
Sure.
So I gave an entire keynote on this topic, poking holes in this, along the lines of what you're also mentioning. But from a more constructive standpoint, what I find remarkable here is that these models can actually do tasks that they have not been trained for as part of their in-context learning abilities. And there you give it an example of the task, kind of task that it has not seen before, and then it is able to do that. But again, this is more in the natural distribution of tasks and not more artificial settings
Because
like
this
this.
is
where
in
you
context
change-
learning, because you get a pattern before you have to do it, right? So it is in context, it's just not in the natural language.
Yes,
doing.
exactly. Yeah.
Okay. So yeah, this is the sort of high level result, headline result. This difference in performance does depend on the task, right? So for the add letter task, where you're just literally extending the sequence of letters, they're really, really good at doing that, and that's unsurprising because that is literally one of the things they're trained to do. Similarly, they're kind of better with the successor task, which is again, doing something to the end of a sequence, than the predecessor task. And then we have these interesting things. I'm not quite sure why, for example, GPT-3 is really good at doing this remove redundant task versus the other models are not so good at that. Yes.
So one other big disclaimer here should be that this performance is contingent on the prompt that you wrote, because there might be different prompts that we can potentially write, which can really shoot up the performance.
Yeah, we did try. We tried a few prompts, and some people have been kind of doing sort of prompt engineering, writing really, really long prompts to get them to be able to do this task, and they are successful in doing that. And one thing actually that I think is quite interesting is that they just gave the body of the paper to in the prompt, and then GPT-4 could do the task. And I thought that was quite cool because actually, we give one example of each task, but we don't give, we don't go through it in full detail at all. So, yeah. Yes.
Okay, maybe a better question here is how much prompt engineering do you need with the people, with the humans? Like when you do this with humans, are they very sensitive to the prompt? Because what you're saying is that the models are super sensitive to the prompt. Are they sensitive to the prompt?
We only did one, prompt for the humans, which was, it looked like this. There were instructions. There was like 3 screens of instructions before, and we gave them an example. A much simpler example than this. It was like AAA, BBB, CCC, very, very simple thing. So we did give it that, but we also trialed that with the models, and it didn't help performance. It hindered performance. Yeah.
So just one strategy that I would suggest trying here would be to ask the model to first generate a rule, description of the rule, and maybe ask it to generate many such possibilities, and then apply that rule and check whether it is correct or not. Because you have one example that you're given.
Yeah,
I think the rule that is consistent.
Agreed. Definitely agreed that you could do a bunch of stuff to make the models do better on this task. But the point of this was not really to do that. It was more just to say, is it to look at the question, is it true that they have this emergent ability? And I think if you start doing that, then it stops being so emergent, maybe.
Martha, one thing that one could do, I don't think Steve and I discussed this when we were back to the SFI, but it just occurred to me, we could completely flip it. We could ask along these kinds of lines, pushing it, tell ChatGPT-4 something better than that, to be quite honest. Give it as a task, come up with these kinds of tasks that, and also associated prompts and so on for the humans and for other LLMs, and actually do so in a way that you think that humans would think are legitimate, that is actually going to make the LLMs do better. You could have that be what you ask.
Just find out what the LLM thinks.
Yeah, just flip things around. We are humans coming up with tasks that we think are somehow appropriate, and we're finding that, oh, you guys, you foreigners, LLMs, don't do well at it. Well, maybe they can do the same thing.
Oh, okay. So for the LLM to come up with a problem that humans can't solve, but that the LLMs can solve.
Along the same lines.
Yeah, that could. Yeah, that would be. Yeah, it would be fun. We could try it. Yeah.
I think that's a syntactically shallow question, sufficiently syntactically shallow question for the language model to answer well.
Yeah.
It doesn't have any semantics to it.
Yeah, but then the
Big
issue
question,
would
but it's
obviously
still
would be,
semantically shallow.
yeah, but the issue would then be, do in fact humans do worse at those kinds of prompts for analogies than the LLM? Is it correct in its answer?
No, but it's very easy to find things that humans do much worse than any of
Yeah,
these
yeah,
things, right? I mean, that's...
But that's the thing, you'd have to find something that you would say, and that a human would find it to be a reasonable task. You wouldn't just say, figure out what the sum of the following million numbers are. Of course the human would fail. But you'd have to play something where you would think it would be legitimate for the humans to go after.
Okay, I'll move on to so like I said to someone, we did do a little bit of error analysis, and so this is quite subjective because it was just me. So basically, I looked through the errors that the humans made, and I categorized them into 4 kind of broad categories, and one is alternate rule formation. So an example of alternate rule formation is where, for example, we expected the answer IJKM, and the participant human or model gave IJKE. So basically there's a rule that it's following, it's a completely valid rule, it's just not the rule that we'd designed. So you could actually mark it correct under some metrics. And then there was like incorrect rule applied, so where maybe it was a successor problem and it did a predecessor answer. So it's just done something, it's followed a different rule. Then there's wrong. So in the case of wrong, the answer that was given would be kind of somewhat related to the desired outcome, desired answer, but it was just wrong, and it didn't. And there wasn't any kind of rule that you could see that it was applying to get there. And then completely wrong was, like a random set of letters or something that is just completely unrelated to the answer we were expecting. And what we saw with GPT-4 was that there was more incorrect rules applied and more wrong rules applied, and more wrong answers. So here, for example, so what am I saying here? This is a predecessor rule. Oh yeah, so this would be a case of like incorrect rule applied maybe. So here, it's a predecessor problem, but instead of going 1 forward, it's gone 2 forward. So it's gone from I to G there instead of from I to H. So it's done something kind of in the ballpark, but it's wrong. And then here, can't remember exactly how I've categorized this one, but this is an interesting one. So here it's a successor problem. And here the alphabet is permuted a bit, and so B is in the place of N. And so it should have answered KLMO, but in fact it answered KLM C. So it's doing successor, but it's doing successor on the unpermuted alphabet instead of on the alphabet that we wanted it to. So it's basically there, you're kind of taking its knowledge from its training set rather than from the prompt. Is there a question?
The output vectors of these models are dictionaries, right? Probabilities that are mapped to
Yeah.
dictionaries. So it'd be interesting to know whether you were getting the first and second.
Yeah, I haven't looked at that, yeah.
So something like GPT-2,
Yeah.
you'll be able to take a look.
Yeah, GPT-2 can't really do these very well at all. Maybe if you made them really simple, it could, but it's not very good.
Yeah, you can query the tokens that are used,
Yeah.
even for.
Oh, can you?
You're right, you're right.
Yeah. So yeah, that would be interesting to look at as well. And then with humans, there was more alternate rule formation, and then more completely wrong. And the completely wrong ones were often where they just put question marks and just said, I don't know, which GPT-4 didn't do. So there's kind of a characteristic difference there. Okay. So yeah, conclusions for this part. Basically, we find that GPT models don't solve letter string analogies in the way that humans do. Performance is worse than humans overall. It differs by task type. The types of errors made are characteristically different. And we've got ongoing works into the other analogical reasoning problems that I mentioned, and that should hopefully be out really soon. So keep an eye. Cool. Okay, so yeah, I won't do the whole of the talk. I'll just probably do the next part on vision language. But yeah, so basically there we were looking at the kind of capabilities of these of GPT-4 in this kind of abstract reasoning task, but we weren't proposing any kind of other sort of way of doing this. So now I'm going to look at, I'm going to present a kind of quick summary of one of the sorts of things that Sean was talking about. And yeah, and it's the following. So basically, this is a way of modeling language. And we're going to, and I call it, well, I don't call it, lots of people call it it is called the typological approach. And it's called typological because it involves types for words, and you're basically doing logic on it. And this was introduced back in 2010 by Manouche and Bob Cook and Stephen Clark. Also concurrent in parallel and independently by Baroni and Zamparelli, although not with this technical background. So in this typological approach to language, we do the following. We basically want to set up a grammar. We just specify a grammar, and we're going to have types N for noun and S for sentence. And each of these types, N for noun and S for sentence, has a left and right inverses, such that if, for example, the type XL occurs to the left of the type X, then it can reduce down to 1, the kind of empty type. And similarly, if the type XR occurs to the right of the type X, then that can also reduce down to 1. And we can build complex types through concatenation. And this is an example of one of the symmetric. Well, it's a monoidal category of the type that Sean was talking about earlier. And yeah, so we built, and this concatenation is, so in this case, the tensor product that he was talking about is concatenation here, basically. So, no, I know, it's not symmetric. It wouldn't work if it was symmetric. Yeah, so basically we model words using their types, okay? So nouns are modeled with type N, sentences are modeled with type S, these, and then words like adjectives and nouns are modeled with types that are kind of these concatenations of other types and their adjoints. We apply these reduction rules that we have here, and if we can write out a string of types, and by applying the reduction rules get down to a type S, that each of these each of these wires here, which is kind of exactly the same thing as the kind of wires that Sean was talking about. If when these reduction rules look like these sort of cups here, if we just end up with one hanging wire and it's an S, then the string of types is grammatical. So that's kind of purely symbolic there. All we've done there is specify a grammar for a language.
So Mark,
Yeah.
about this. First of all, how accurately do humans follow this, and how much does it vary from one human natural language to another one? Also, where does it fall in the Chomsky hierarchy?
Manoush, do you know where it falls in the Chomsky hierarchy?
People translatable to something called Lambert calculus, which is context-free grammar.
Okay, so it's all the way over to context-free. Yeah, I know that. Okay, so it's all the way context-free. Okay.
Yeah.
But then what about the other question about how much accurately humans follow this?
Well, if humans spoke always grammatically in a particular language, then this particular instantiation where you've just got N for noun and S for sentence is not really going to model human language, but there's a lot of work looking at more linguistically accurate versions of this.
I can say something if you want.
Sorry?
So Lambert suggested this formalism, which is called primitive grammars. He also he went through psycholinguistic literature and showed that humans are not, when you use trees to analyze syntax like Chomsky does, you have to draw parse trees. And these parse trees can get quite deep. And humans can effectively only go 2 or 3 levels down. So they're not so good at understanding a deep tree, and they're much better in understanding these kind of diagrams which are linear.
Okay, so the fact that this is then equivalent to context-free means that this is in some ways a better representation to capture the actual processes of humans going after context. Are all context-free languages, can they be expressed in this way, or is this just a subset, all of them? So
They're equivalent.
So they're equivalent. Okay, interesting.
Yeah. Okay, so this is purely symbolic. And what we want to do is we want to choose some kind of semantics which has the same structure as the grammar, where we can just plug in some kind of semantic representation on the top. And in this paper, the main thing that was proposed, and also in this paper, is to use vector spaces. Okay, so each of these letters here is a vector space. Now this tensor product, the concatenation of these, is now actual tensor product of vector spaces. And then we can plug in particular states in that vector space. So a state, in this case, in the case where you've just got one wire, is a vector. Where you've got 2 wires, it's a matrix. And then where you've got 3, it's going to be a sort of cuboid of parameters. So now we have, this. So the title of this Baroni and Zamparelli paper was Nouns are Vectors, Adjectives are Matrices. And we have this idea that basically the grammatical structure of words in the language is represented by the kind of structure of the words in a particular vector space. Okay, so that's one sort of compositional model that I'm going to use. And then the other one is these things called role filler bindings, which Sanjoy talked about on Monday, I think it was, if you remember that talk. So in this sort of model, we again have a kind of symbolic structure for, in our case, language, which we map down onto a vector or neural or statistical structure. And so now the symbolic structure looks as follows. We've got symbols so if we've got dog chases kid, we've got symbols for each of the words in the sentence. This is kind of the content of the word. We've got symbols for the types of the words in the sentence. So we've got subject, verb, and object. And then the content and the type are kind of are bound together, in this case using this slash. And then these role filler bindings are then collected together on the symbolic level in a set. So we have a sentence is represented as a set of role filler bindings. It's a set because the role, the aim is that the role should represent any sequence if that's necessary. Yeah. So in this case, it does because subject, verb, and object are combined together in that order. But you could equally like put this over here and this over here. And yeah, in a different language, you'd have a different representation. Yeah. And then these get mapped down to, so each of these individual, so in this particular representation, the fillers, so the content symbols and the roles each get mapped onto vectors. The binding operator, which is written as a slash here, is mapped onto tensor product. And this kind of collection into a set is mapped onto addition. You're just adding together these things that you've built. There are lots and lots of variants of this. And the variants tend to be based on like, so what entries you can have in your vectors, what the binding operator is. I don't know about the collection operator, like whether there's always, you can change that as well, can you? Yeah. Yeah. Okay. Okay, yeah. So each of these, you can have lots of, there are lots of different kind of instantiations of this with different sort of things that you choose for each of these.
Sorry, so are these vector spaces of a vector space that are subject, are verb and are object?
These are vectors. These are literally like vectors.
And the R's, the rows are
also vectors.
They're also vectors.
Yeah. But they could be in different spaces.
So this is not a linear combination, no.
So basically, so Smolensky, so for adding things together, Smolensky does something where he kind of creates a sort of much larger space to do the addition in. If you use holographic reduced representations, you do something to this binding operator to make it so that everything's mapped into one space. So there's always a way of doing this. Just like in the reals, I think, or you can have complex, or you can have like ones and zeros. Yeah.
Yeah, I was just going to say the only difference is when Smolensky originally did it, it was a vector outer product, and so when you did a binding, you went from n-dimensional vectors into n squared into n cubed.
Yeah.
And so the innovation that Plate and Canerva came up with was to make the operations, the space of representations was closed under the operations.
Yes.
And so Tony Plate did it with circular convolutions.
Yeah.
And Canerva did it with just bitwise XOR.
Yeah. Yeah. Oh, I didn't fill this out. I was going to have a slide full of applications, so I was going to say, for example, Marnouche's done like a whole bunch of work on this, looking at things like lexical ambiguity, looking at looking at, when you say Bob likes his code and Jim does too, what's that called? Enough for a resolution. Yeah, so lots and lots of like linguistic phenomena that you can look at using this. And similarly with role filler bindings, there's been lots and lots of applications with this. Tom McCoy, who I think Tom Griffiths is a collaborator with, has done a bunch of work looking at how and whether recurrent neural networks kind of represent these role filler bindings somehow and so on. So there's a lot of work in this area. And so this is kind of just extending that out a little bit. So I was interested in applying these kinds of compositional models in vision and language. And so again, motivations, like this is a year or two ago now, so they've got a bit better at this, but vision language models are not very good at, for example, encoding spatial concepts. And so what we wanted to do was to look at, well, what can they actually do? And we built this concept binding benchmark, which is just based off this clever data set, but it's kind of a simpler version. And so in this concept binding benchmark, okay, so as humans, right, we can look at this picture here and we can see that there's a yellow sphere and there's a gray cube, and we perceive each of those things as a kind of a whole, right? And our question was, well, do vision language models, like there's this one called CLIP, does that do the same? Can that do that as well? So in this data set, it's a kind of labeling, it's a labeling task. So basically we give pictures with just one image in and one shape, and it has to pick out the correct label out of a bunch of potential labels here. For this 2-object data set, it has to pick out the correct label from, well, obviously the correct one, yellow sphere, and then these kind of difficult distractors of like gray sphere and yellow cube, where we've swapped over the attributes. And then similarly, we had ones with 2 objects where the labels are now spatial labels. So now the correct label of this is cube left of cylinder. There's also, but then we also ask it to choose between cube right of cylinder, so we've swapped the orientation, or cylinder left of cube, so there again it's the same words but the wrong way around, and so on. And so and then we have a training split, validation split, and then our testing split is in a sort of generalization scenario. So we hold out a bunch of shape color combinations or like shape orientations, and test on those held out images. And obviously what we hope is that the compositional models will be able to do this, and unfortunately, I'll get it over with, they can't, which is really frustrating, really frustrating. So I'm going to keep working on it and see if, there are some things we can do to make these better. But anyway, but CLIP can't do it either, so there we go. Okay, so what is CLIP? So CLIP is this model that was introduced by OpenAI a few years ago. It forms the backbone of software like DALL-E, which does image generation in GPT-4 and so on. The version that we were working with is the open source version, so it's obviously been massively improved since this iteration, but this is what we had to work with. So CLIP is basically trained, and then in the task that you give it, it's given an image. It puts the image through an image encoder, spits out a vector for the image, and then you can give it a bunch of kind of potential labels, which you wrap in a nice in a sort of sentence. You put these sentences through the text encoder, so it gives you 10 potential 10 vectors, one for each sentence. And then what you want is that the vector that has the highest inner product with the image vector is the correct label. Okay, so you're trying to put these into one shared space. And so what we did was we kept the image encoder, but we replaced the text encoder with these compositional models that we that I just talked about. So we have this kind of typological model, we have a role filler model, and then we have a few other models, so addition and pointwise multiplication, where we're just doing kind of pointwise operations on the vectors. Okay. So so like I say, what we would hope is that these do better. Unfortunately, they don't really, but I think it's still kind of interesting to see the differences in performance. Okay, so results on this single object and two object data set. The first thing to note is that on single object, the frozen clip model can already do like really, really well because it has been trained on these sorts of things. And what we find is that additive kinds of models, so we've got the like pointwise addition of vectors and these role filler models, which are also quite additive in this kind of collection sort of operation, also do pretty well, right? They can generalize to unseen label combinations. And this is not surprising, right? Because all you need to do is see that there's something blue there, something cuboid there, cubical there, and sort of add together those things to get this representation. But then what we anticipate is that then on the two object, it's not going to work quite so well. And so, yeah, frozen clip is very, very bad at this, right? It can't, without any fine-tuning, clip can't do this task at all. With fine-tuning, it can start doing the task, but it can't generalize. Okay, so we get it can't generalize to these unseen labels. And then the best results that we got here was with this multiplicative model with kind of pointwise multiplication of vectors, and this typological model, so the kind of matrix vector multiplication, where again we can get really good results on training, but then they're still not able to generalize very well. I think what we were interested in here was the fact that you get these different behaviors as well on different tasks, right? So here the clip model seems to be, has the similar headline performance to these additive models, whereas on this task, this fine-tuned clip model has similar headline performance to these multiplicative models.
Yes, so for the fine-tune row, you took original model and fine-tuned it, right?
Yeah.
And the train is what you got on the training data set?
It is, yeah.
But, so this is literally the training data, right?
Yeah.
So you had the validation data set, which was somewhat different, right?
Yeah, so it's a bit annoying. We didn't have an in-distribution validation data set. We had a validation data set that was out of distribution in the sense that it hadn't seen those label combinations before. So I think if we had a validation data set that was the same distribution as the training data set, it would do up at these levels from like subsequent experiments that we've done.
So what I wanted to say is that if you do not have the validation data set, you validate your fine-tuning procedure itself, then that's problematic, true. Because you don't know if the hyperparameters you're using are correct, right?
Yeah, I mean, we were validating on the ability to generalize to out of distribution, I guess.
But this decreased, right? So you had the original score and you fine-tuned, and it got worse, right?
Yeah. So, I mean, it doesn't. Yeah. I mean, yes. This is something that people. So, I think, It's unsurprising that it does a bit worse because we're testing it, because we're sort of telling it like this is This is the kind of distribution of data we want you to look at, and then we're testing it on out-of-distribution data. So it's not surprising that the out-of-distribution... Yeah, sorry. Yeah, we can talk after. Yeah. Okay, and then finally, on the relational results, we have, again, a similar sort of thing. But here on fine-tuning, we can't even get up to... we can't get even a good performance just on the training data set for these spatial problems. For the typological model, we can actually, for technical reasons, we put a sort of lower thing there, but it does actually go up to like 99% accuracy here. So so again, we see a similar sort of thing. So the concept binding tasks are hard for CLIP. They're also frustratingly hard for compositional models. And again, this relational task where we're asking it to pick out particular spatial relations is kind of particularly hard for CLIP models and for these compositional models. Let me just kind of whiz through to the end. I mean, we did a little bit of analysis looking at, the problems with CLIP is that, first of all, text prompts are not adequately distinguished even after fine-tuning. Image embeddings can also be ambiguous. They're a bit less ambiguous, but they also are ambiguous. And we've also started doing some work looking at diffusion classifiers rather than CLIP. And with diffusion classifier, that does start getting kind of better results on these unseen things. Okay, so I'm going to stop there and take any more questions that people might have.